Is time the fourth dimension? The idea that time is the fourth dimension is a helpful way to understand how time and space interact. But it's not entirely accurate to say that time is simply a fourth dimension, in the same way that length, width, and height are dimensions. Time behaves differently from spatial dimensions and plays a unique role in the framework of spacetime. So, while it's often grouped with spatial dimensions for conceptual clarity, time itself is fundamentally distinct. Let's explore why time is not the fourth dimension, as it is often referred to as. In our everyday experience, we can move freely in three-dimensional space, forward and backward, left and right, up and down. These spatial dimensions are all similar in nature. They allow movement in two opposite directions along a continuous axis, and we can choose where to go in each of them. Time, however, is experienced in only one direction, forward. This is called the arrow of time, and it's tied to the concept of entropy, or the tendency of things to move from order to disorder. While spatial dimensions allow for freedom of movement, time has an inherent directionality that we cannot reverse. We are bound to move forward in time, and we cannot choose to go backward or to a specific moment in the same way we can choose a point in space. In the theory of relativity, time and space are unified into what we call spacetime, a four-dimensional fabric that combines both spatial dimensions and time into a single framework. In this model, time is treated as a dimension for the sake of mathematical convenience, but it behaves differently from the other three. A key difference between time and space is how they respond to relative motion. According to Einstein's theory of special relativity, time slows down as an object approaches the speed of light. So, if you're traveling close to the speed of light, you would experience time more slowly compared to someone who is stationary. This phenomenon doesn't occur in spatial dimensions. Distances don't slow down or speed up depending on how fast you're moving. Similarly, objects moving close to the speed of light appear shorter in the direction of motion to an outside observer. This affects spatial dimensions, but not time itself. These effects are a consequence of the fact that time and space, although related, are fundamentally different in how they interact with motion and gravity. Perhaps most importantly, time has an irreversible quality that spatial dimensions don't have. We refer to this one-way progression as the arrow of time, which is tied to the second law of thermodynamics. This law states that the entropy, or disorder, of a closed system tends to increase over time, which gives time its directional flow. This phenomenon doesn't exist in spatial dimensions. There is no inherent forward or backward in space. In other words, while you can move back and forth in space without consequence, you cannot move backward in time in the same way. Because time's progression is governed by entropy and thermodynamic processes that only allow it to move in one direction. Time also plays a unique role in causality, the relationship between cause and effect. Events occur in a specific temporal order, where a cause must precede its effect. This is essential for the structure of reality as we understand it, and it's something we don't see in spatial dimensions. For instance, in space, the order of your steps doesn't affect the result. You can choose to move left, then right, or right, then left, and end up at the same place. In time, however, events must happen in a particular order. You can't have an effect occur before its cause. This causality constraint is a fundamental aspect of time that distinguishes it from spatial dimensions. In physics, time is treated mathematically as a separate component in equations. When physicists describe objects moving through space-time, they often use four-dimensional coordinates. 3 for space, noted as x, y, and z, and 1 for time, noted as t. But they apply different rules for time than for space. For example, in general relativity, the metric for calculating distances in space-time includes a negative sign for time components, as shown in the metric tensor. This negative sign is not arbitrary. It mathematically represents the difference between time and space, showing that they don't function identically. This negative treatment of time, often called imaginary time in complex number terms, reflects its unique properties within the fabric of space-time. Some physicists suggest that time is better thought of as a parameter rather than a true dimension. A parameter is something that defines conditions or sets limits, rather than providing a degree of freedom to move in like spatial dimensions do. In many physical theories, time is treated as an ordering system, rather than a dimension through which we can physically travel. In certain theories, such as quantum mechanics, time does not behave as a dimension in the way spatial dimensions do. Instead, it provides a sequential order for events. This view supports the idea that time is a special kind of measurement, necessary for tracking changes and sequences, but not identical to spatial dimensions. The idea of time as a dimension is useful for understanding relativity and the interconnected nature of space and time. But it's not a dimension in the same sense as length, width, or height. It is often called the fourth dimension for convenience, but it behaves differently under the laws of physics and has an irreversible forward direction tied to entropy. Instead, time serves as a special coordinate that orders events, giving structure to change and allowing causality to unfold. These differences highlight why time is a distinct entity and not simply another dimension like the others. We thank you for spending time with us in this third dimension and invite you back for another episode of A Godless Universe.